Welcome to the Thermoset Resins lectures on silicones. There are two separate silicones PowerPoints, but these are kind of short, so I'm going to put them into one video. In this particular PowerPoint, I'm talking about history and nomenclature, silicone structures, forms of silicones, and silicone production. The silicones are our first specialty thermoset, and we're going to have to identify the characteristic group of a silicone. It's probably a little different than anything else we've talked about in terms of polymers. The role of characteristic and substituent groups in determining properties of silicones, different forms of silicones, alkyl to silicon ratio, properties of the different forms of silicones, and of course, applications. So, the father of silicones is F.S. Kipping, and he first succeeded in synthesizing an organosilicone compound in 1898, and he's the one that coined the term silicones. What he was trying to do is make ketone functionalities on the silicon itself, but it didn't work. What he ended up giving was substituent groups, but he kind of stuck to the, I'm going to call it a silicone, you know, like a ketone, but it's not really a ketone. A further development was made possible by direct synthesis of methychlorophenyl by Muller and Rochow in the early 1940s. And the first silicone product was a paste for protecting aircraft ignition systems against moisture, and it was produced by Dow Corning, who still does the majority of silicone chemistry to this day, in 1944. In 1947, S. Nietzsche from Wacker Industries started research into silanes and silicones. Wacker Industries is still Dow's biggest competitor when it comes to silicones. In 1952, silicone resin products included silicone fluids, fluid emulsions, anti-foaming agents, impregnants, pastes, and release agents. And then work also began in 1952 on silicone elastomers. High-temperature vulcanizing silicone rubbers were sold in 1953. And as of 1954, room temperature vulcanizing grades were also added. In 1970, you had two-component silicone rubbers being produced. And so that's kind of where the technology stands now, and I'll define that a little bit further. First, we have to do some silicon nomenclature. So silicone is a resin. Silicon is the element, Si on the periodic table. So that's what forms the backbone of our polymers. And in the past, we've dealt with carbon-based stuff. Now we're doing with inorganic backbones. So this is a little different. Some things are the same, some things are different. So we have to kind of back up and define this stuff. The silicon is the most abundant element on Earth, but it's usually found in the form of silicates. In other words, SiO4 with a -2 charge. And this is in mineral substances like clays, glass, ores, rocks, stuff like that. A silicone is a polymeric synthetic material which has a siloxane backbone and organic groups attached to those silicon atoms. And this usually refers to the total resin. So not just the polysiloxane, but all the other junk you put in it, like fillers and whatnot. The siloxane is this bond, is this SiO-Si bond. And that's a siloxane is something that has that regular structure. So silicon, oxygen, that alternating structure in a chain. This is what it looks like. So it has, here's your silicon atom, here is your oxygen, and here's another one. And one thing I'd like to call attention to is this has 4 bonds to it. Weird, kind of like carbon. So it has 4 bonds to carbon, but it's a whole different element, so it behaves a lot differently. The siloxane group is extremely flexible, and because it has a structure that's similar to like quartz or granite, what that actually provides in the resulting polymer is extremely good thermal oxidative stability. So much more so than something with carbon. So again, that thermal stability is produced by the SiO-Si backbone. And then you attach substituent groups to that. So alkyl groups, aryl groups or aromatic groups, vinyl groups, double bonds you can polymerize through, silanols or OH groups attached directly to the silicon atom, and then hydrides or hydrogen atoms attached directly to the silicon atom. So the substituent groups that you choose give you other properties in the remaining polymer. So here we go. All kinds of different substituent groups. So here's your repeat unit. So this is a polydimethylsiloxane, dimethyl 1,2, polydimethylsiloxane. So here is, so here is your repeat unit. You can silanol terminate these. So here we have SiOH groups. You can vinyl terminate these. These groups can then go on to do free radical polymerization to cross-link. You can have vinyl to backbone, so you can have it attached here. Or you can have methyl hydrodimethylsiloxanes. So you have a hydride present here, and then you can have a comonomer here, and then it can be hydroxyl terminated or all sorts of things. I've worked with a wide variety of these to make silicone elastomers. So as I mentioned before, silicon, the atom, has a valency of 4. Carbon also has a valency of 4. What a coincidence! But it exhibits something else called a coordination number. This is an inorganic molecule, and it has a coordination number, meaning that it has the ability to associate with 6 things, but not in a covalent bond type situation. This is more electropositive than carbon, and so the bond of silicon and carbon and the bond of silicon and oxygen are different than say a carbon-carbon or a carbon-oxygen bond. Carbon-carbon, carbon-oxygen, those are definitely covalent bonds. A silicon-carbon or a silicon-oxygen bond are partially ionic, and so they have a higher degree of freedom, and then that degree of freedom also means really flexible chains, extremely flexible chains. So they're much more flexible than a carbon backbone, even if you have like a carbon ether backbone. So CO, SiO bonds are even more flexible. So silicones can occur in a wide variety of forms. They can be fluids, elastomers, or resins. And the physical form of the silicone is dependent by 3 factors: the molecular weight, degree of cross-linking between the chains, and the type and number of organic groups attached to those silicon atoms. So the production of silicones was eventually done by GE, and this was a batch reaction. You can make aryl or alkyl halides in the presence of a catalyst like copper and silver, copper for methyl and silver for phenyl chlorosilanes, and then you can get a reaction that gives you a monochlorosilane or a dichlorosilane or a trichlorosilane, and then you hydrolyze those methylchlorosilanes into a polymer. What the heck do I mean by that? This is what I'm talking about. So you take quartzite. Yes, this is your mineral in the presence of carbon, and that gives you elemental silicon and 2 moles of carbon monoxide. So you have your elemental silicon in the presence of a organohalide, and that will give you a silicon that has up to 4 of these halide groups attached to it. Then you can do hydrolysis to form your silicone. So this is what I mean. If you have a trimethyl, if you have something that's trimethyl, this is monofunctional, and you can only get disiloxanes. Fun fact, this is the active ingredient in anti-gas pills. So if you've bought Gas-X or something like that, this is what you're buying, a dimethylsiloxane. That is the anti-foaming agent that works in your gut to help you avoid embarrassing social situations as a result of gastrointestinal distress caused by gas. So that's one of the consumer products that you probably already used. If you have a difunctional dichlorosilane, you can make linear polysiloxanes with that. And if you have this particular monomethyl, this is trifunctional, and then you can make it cross-linked gel. You can also do a mixture of these and give you different situations. So I am going to open the next one, and we're going to continue with silicones. So the R group to SI ratio is what we're going to talk about. So the ratio of those organic groups that is attached to the silicon, properties, and then applications. When you're characterizing a silicone, it's based on the alkyl to silicon ratio, or R to SI ratio. The closer that R to SI ratio is to 1:1, the higher degree of cross-linking. So, for example, if R to SI is 1.5 to 1, it has a higher degree of cross-linking than R to SI of 2 to 1. A typical silicone fluid will have an R to SI ratio of 3 to 1. A silicone resin will typically have 1 to 1. And then elastomers will typically have an R to SI ratio of 2 to 1. It'll be in a linear polymer if it's a true elastomer, in other words, thermoplastic in nature. Resins themselves are heavily cross-linked and therefore are closer to 1 to 1. So, commercially available silicone fluids are usually colorless fluids. They can have a wide variety of viscosities, so 5 to 2.5 million centistokes. You have dimethyl polysiloxanes, so shown here. Again, that's the liquid component inside of your gas gel tablet. Methyl phenyl polysiloxanes, and then methyl chlorophenyl siloxanes. So here's your chlorophenyl, here's your phenyl group. And you choose these substituent groups for different applications. Methyl groups usually give low crystallinity and enhanced temperature stability. The nice thing about a polydimethylsiloxane is that it is the most widely used. It has a really unique characteristic in that it's highly compressible. So most fluids aren't really compressible, like water isn't really compressible, so this is a fluid that can be compressed. So if you have a 10 centistokes viscosity fluid, you can experience a 15% reduction in volume without changing it to a solid. And that can be very useful in some applications. That's because of that high degree of freedom around that silicon atom, extremely flexible. You can squash that molecule and without negative repercussions. And your substituent groups can move around the backbone easily because of the nature of that bond. Polymethylphenylsiloxane, that's partial aryl substitution of methyl groups. This gives improved low and high temperature stability. So low temperature stability, you disrupt crystallization, that's good, and then better high temperature stability. So these can be -60 to 250 degrees Celsius. You also get improved compatibility with polar organic groups. It's also less susceptible to attack by oxidizing agents if you replace one of those methyl groups with a phenyl group. And then polymethychlorophenyl, the halogenated substituent is used to produce silicone fluids, methylchlorophenyl polysiloxanes. And under harsh conditions, these are preferred lubricants. And they give better resistance to halogenated and aromatic solvents than their counterparts. If you really feel like doing viscosity on these, you can calculate the intrinsic viscosity. Again, the viscosity of the fluid can vary widely depending on the application. And I just bumped my camera. Technical difficulties, hold on. Sorry about that. So here is a viscosity table. So you see there's a change in the volume coefficient of expansion, change in the flash point. If you get higher viscosity, higher molecular weight. Dielectric constant goes up somewhat, dielectric strength goes up somewhat, and you get a slightly more dense silicone fluid as your viscosity and therefore molecular weight increases. So here is your compressibility table. So as you apply the pressure, you can see how the properties change. You can only really do this with mineral oil up to 2000, so this is why a silicone fluid is advantageous as opposed to a traditional lubricant or water. Silicone fluids are insoluble in water. They are soluble in low molecular weight alcohols or glycols and higher molecular weight hydrocarbons. They can also be soluble in petroleum, fatty acids, and vegetable oils. They're insoluble in water, low molecular weight alcohols, higher molecular weight hydrocarbons, and petroleum, fatty acids, and vegetable oils. They're soluble in hexane, heptane, benzene, xylene, chlorinated hydrocarbons, and methyl ethyl ketone. The things that they are actually soluble in are kind of nasty. So if you need something in a solvent, you're going to be handling something rather hairy. The silicone elastomers, these are linear polydimethylsiloxanes with very high molecular weight. 500,000 grams per mole or higher. These are usually linear polymers that have been cross-linked after fabrication. So they can be elastomeric, but in terms of thermoplastic, but usually they're processed and then cross-linked through a second step. Cross-linking usually takes place in the presence of an alkaline material, so benzoyl peroxide or butyl perbenzoate at elevated temperature. You can also UV cure these, and then they usually incorporate silica-type fillers. I have had 3 graduate students do research on this. A polysiloxane by itself is very weak. You almost always need a silica to fill those. You have to enhance the strength, and silica interacts very well with a polydimethylsiloxane. So that's typically what's used. Silica can range anywhere in size from 0.03 to 0.03 millimeters. All kinds of different silica fillers that you can use, which we've discussed in other lectures. But these are almost always reinforced because they'd be too weak to be useful if they weren't. There are 2 different forms. There's room temperature vulcanizate or high temperature vulcanizate. Room temperature vulcanizes or cross-links at room temperature, and high temperature vulcanizes at elevated temperature or cross-links at elevated temperature. So you need to elevate the temperature to cure it. So RTV, or room temperature vulcanizate, come in 1-component and 2-component systems. In a 1-component system, this uses atmospheric moisture to cure it into a network, and there's two types of those one component systems. There's an acetoxy and an alkoxy. If you've ever had the joy of caulking your tub with a silicone caulking agent, you've often used an alkoxy RTV silicone. And it has that kind of old lady smell. I don't know how any way to describe it other than say old lady smell, but that's methyl alcohol that it gives off as a byproduct. If you're using an acetoxy, you will know it because it gives off acetic acid as a byproduct, which smells like vinegar because it is vinegar. So alkoxy are usually preferred because they don't smell as bad. Also, they don't give off acid, which is corrosive. So they both use atmospheric moisture to cure, but there's other aspects like how fast they cure, the rate of cure byproducts, adhesion, tack-free time for your kind of working life, corrosion potential, and of course odor. So your tack-free time for an alkoxy is 2 to 4 hours. That's your 2-hour shower-ready bathtub silicone. Your full cure time is about 72 hours. Acetoxy is much lower than that. So your attack-free time is really short, 15 minutes, and then 24 hours to cure. Your adhesion to most surfaces for an alkoxy are excellent. When it comes to an acetoxy, you get excellent adhesion on glass and ceramic, pretty good on iron and steel, and you don't want to use it on copper. They're pretty good on polycarbonate and acrylic. They're okay on PVC. The odor during cure, methanol doesn't smell great, but it smells better than pungent acetic acid. And an acetoxy, which gives off acetic acid, can cause corrosion. So, whereas alkoxy or methanol doesn't. So if corrosion is something you want to avoid, use an alkoxy. Most of these one-component RTVs are effective in applications of 1/4 of an inch thickness or less. That's why your bead of silicone caulking needs to be kind of not big and globby. It needs to extract moisture from the atmosphere, and then it has to diffuse through the silicones. So if it's super thick, it won't actually diffuse. You won't get a good seal. And these are your formed-in-place gasketing, otherwise known as bathtub caulking. So sealants and adhesives as well. You can tell by my enthusiasm how much I love bathtub caulking. In your 2-component RTVs, these are often silanol terminated polymers, and then they're further cured with silicate esters as a second component. There's a mixing ratio of typically 10 to 1, and this is done in the presence of a catalyst. Tin octawate or dibutyl tin dilaurate or some sort of UV catalyst that's mixed together in a 2-component system. So here you have low molecular weight monomers with reactive end groups in the form of your silanols. Here you have your silicates. You mix them together and you cause cross-linking that looks like so. These can be 2 different mechanisms of curing, condensation curing. So water and other byproducts are formed, and this is recommended for systems that aren't sealed. In other words, a small molecule has to be given off and then evaporates, so you don't want to seal it off. And then there's addition cured. Addition cured is the stuff that I've worked with. These don't give off byproducts. They're high strength, non-corrosive, deep section cures. In other words, really thick, big, rubbery parts can be made out of this. And they can be made in completely sealed systems because you don't have to worry about getting rid of water or other small molecule byproducts. So here are some typical condensation cured RTVs. Fairly similar properties, the big thing being the very wide temperature range. So condensation cured RTVs tend to have a lower temperature range, so even super low temperature properties. Addition cured RTVs tend to have, they don't go to as low a temperature as the condensation cured RTVs. Now there's HTVs. So RTVs are room temperature vulcanizate. HTVs are high temperature vulcanizate. So in this case, you take a silicone elastomer with a crosslink at a methylene, and then you have some sort of radical that's created either from benzoyl peroxide or maybe a UV degradation. You heat it up, and then you get these methyl linkages that crosslink. And that's how you create your high temperature vulcanizate. Silly putty is a high temperature vulcanizate. It is modified with boric acid and fillers and plasticizers, but it is an HTV silicone. It has that high bounce and viscous flow on gentle application of pressure. It's a super fun, endless hours of entertainment that comes in a red egg. The application temperature for HTVs is -50 to 250 Celsius. So again, a very wide temperature range. Not quite as high as some of the other RTVs, but still a fairly wide temperature range. Silicone resins are made batchwise. by a blend of chlorosilanes, and you're dealing with very low R to SI ratios, so 1.2 to 1.6 to 1. And these are catalyzed by triethanol amines and metal octates. Typical silicone resins are methyl phenyl silicone resins. They're used in heat-resistant glass cloth laminates for electrical applications often. They have good heat resistance. They do have lower mechanical properties than other thermosets if they are unfilled, and so they're typically filled. But these have high hydrolytic resistance and good electrical insulating properties. The nice thing about these, the reason you'd use them as opposed to another thermoset, is they're very wide range of critical use. So very low to very high temperature, very low water absorptivity, and they're often water repellent. And they have you can vary the form. You can do flexible or rigid depending on your alkyl groups. You can also get transparent. So there's a lot of formulation flexibility. The resins themselves had good electrical insulation properties. They're chemically inert. They also have very good weatherability. They are self-extinguishing to slow burning. So these are going to be used in situations with a lot of heat. And they have a high degree of slip or lubricity on most rubber or plastic surfaces as well. Nothing really they have that kind of non-slip, that's kind of slippy property. Oh, disadvantages. Unfilled, they have very low strength. They are relatively high cost. And because they are made with chlorosilanes, they often are susceptible to halogenated solvents. When it comes to applications of silicone fluids, these are often used for anti-foaming agents, like in your gut with GasX, but also in polyurethane formulation. Hydraulic and dampening fluids, prevention of transmission vibration, additives in paints and oils and inks, car and furniture polishes, they cause low surface tension. Mold release agents, paper coatings, dielectric coolants, glass and fabric finishes, heat exchanger fluid. They can also be made into surfactants for other applications. They're also good for high temperature lubrication of rubber, plastics, gears, ball bearings, valves, vacuum pumps, and what have you. Silicone resins are present in granular or fibrous forms with outstanding electrical and thermal properties. They're often used for encapsulation of electronic components, mineral glass filled. The adhesives and sealants, they are limited by high cost, but they are used because of their high temperature and very low temperature properties. So very flexible at low temperature, very stable up to high temperature. And are used in, of course, sealing, gasketing, and caulking.